In the last lecture, we defined something called work, which allowed us to define something called energy. And what we'll talk about today is sort of the fundamental principle regarding energy, which is that of energy conservation. We'll see how we can use that to solve some problems. And we'll see how it comes about due to something called a conservative force, which defines something called a potential energy. And potential energy, together with kinetic energy, which we defined last time, the energy of motion, forms something called mechanical energy. And most of the problems we'll be doing will have to do with conservation of mechanical energy. So just a quick overview. We'll define what a conservative force is and how it has an associated potential energy function. We'll talk about the two primary examples in which we'll deal with conservative forces, and those are the force of gravity and the force of the spring. I'll talk a little bit about non-conservative forces and how we might deal with them, and then we'll write down the statement of conservation of energy. It comes out of the Work-KE Theorem together with the stuff that is defined here. And then we'll do three examples. So one is just a simple example where you can see that we can do some kinematics problems that we were doing back at the beginning of the semester in maybe an easier way. We'll do an example which involves a non-conservative force, friction, and then we'll do one that involves both dynamics and springs and conservation of energy. Okay, so let's talk about conservative forces. So a conservative force, and this is just a definition, it's a force for which, and let me write it down, the work done by the force over a closed loop path is zero. So we talked last time about what work is, and the idea is that if you do work by a force along some displacement, then you have to look at the force acting, so maybe it's with gravity acting down, and you're moving a ball upwards and to the right. Well, you have to calculate F dot delta R in order to calculate that work. Well, what the definition of conservative force says, if you take that ball and you move it around in a closed loop, so it's going to go along some delta R displacement vectors like this, but end up back at the beginning, then the total work that you find should be zero. And you could state this equivalently as the work done between any two points, so like from A to B, is independent of the path taken. So we talked about how work, as I just said in words, is equal to the force times the displacement. So the work depends on which particular displacement you choose to pick. And there's nothing that says that the work when going from like point A to point C is the same as the work going from A to B to C. So those are two different paths that one could take. Both of them go from A to C, but in the second one you're going to B as an intermediate step. And it's not true in general that the work would be the same between those along each path. But if a force is conservative, so that's what we're defining here, then the work done between any 2 points is independent of the path that you take there. And we'll show how that works for gravity to prove that gravity is a conservative force in just a few minutes. So if you have a conservative force, then that allows you to define something called the potential energy function. So let me just write down the definition, then we'll talk for a moment about what it is. If you have a conservative force F, then we can define UF which is a function of the position, so the position in space. And UF is defined not directly in terms of its function, but in terms of the difference between 2 points. So you could call that like UF at the final point minus UF at the initial point. That's what we mean by the delta. Both of those things mean the same thing, and here's the definition. It is minus the work done by the force in going from the initial to the final point. So what does this have to do with conservative forces? Well, we said that a conservative force, it doesn't matter what the path is that you take as you go from one point to another. So on this right-hand side, you can see that it doesn't specify which path you take. It just says you go from one position in space to another position in space. So that's like you have one point, the initial point here, and then you have another point, the final point here. And it doesn't matter if you go from here to here, or from here to here, or from here to here. The work that you calculate done by the force will be the same because it's a conservative force, and that means you can assign a number from going from here to here, and that doesn't depend on the path. And that number is what we call the difference in potential energy for the potential energy function associated to the particular force that we're talking about. I realize this is all sort of abstract, but we'll make it very clear in terms of gravity and springs and how one uses it. So the idea is a conservative force somehow allows you to connect points with work without worrying about the path that you take. And because you can do that, then you can assign a difference in potential energy. And then it'll turn out that the fact that it's a difference just means that you can say that the potential energy is 0 at any particular point you choose, at a point where it's convenient for you to do that. And we'll see how that works out in terms of the specific forces. So we're going to look at two primary examples, and I'll just write them down. The first is gravity, as I already mentioned. So we have the force of gravity vector. It's the force of gravity points down. It has magnitude mg when it's acting on a mass m. And then that determines the work done by the force of gravity. And the work done by the force of gravity, it turns out, doesn't depend on the path that you take. And we'll have a potential energy function, which we'll write as UG. And it turns out that that only depends on the vertical position. So I'm going to call that y, as we normally call it. But basically, y is the axis that points upward out of the center of the Earth. And we'll see how that's defined. And then the other main conservative force is the spring force. So we called that Fs, and it gives us a work done by the spring force, and we'll show that that work is independent of the path, and therefore we can define a u sub s, and we're going to define that function in terms of the x position, which, as we talked about last time, is position with respect to equilibrium. So meaning the position at which the spring is unstretched will be called x is equal to 0. So we'll define these two potential energy functions, ug of y and us of x, and we'll write them down explicitly. But there are other forces that are conservative. So I shouldn't have written a big G here. This is what I meant was the force of gravity little g that we see on the surface of the Earth. However, F big G is another example. So the force between two planets is the force of gravity, and we already talked about how that was really the same thing as the force of gravity we see on the surface of the Earth, and that is a conservative force. There are other conservative forces. One that you'll encounter early in next semester is the force due to an electric field. So the force of an electric field on a charge, that's a conservative force, and we'll talk about potential energy in that case. And there are other ones, but we'll focus mostly on these two right here. So let's prove that gravity is a conservative force. So the way that we do that is that we consider an arbitrary closed path. We said that a force is conservative if you take any closed path and you find that the work done is 0. So we're going to show that. We're just going to pick some arbitrary points. So let's draw a little picture. So we're just standing here near the surface of the Earth. So here's your table with your book on it. And you're watching, I don't know, somehow there's a ball and it's going to move between these 3 points. So it doesn't matter if the ball is in free fall or if the ball is being moved around by some object, maybe by a bird. The question is not the other forces on the ball, it's only about the force of gravity. So we'll look at the force of gravity as it acts on the ball as it moves between these different points. So we're going to take a path, and we'll call this like point A and point B and point C. And we could label some distances here. So let's say that this is like H1. And then I guess we need to say that this is H2. And then maybe we'll need these distances here, D1 and D2, just to specify those arbitrary points. But I won't give values to H1, H2, D1, D2, because we want to say that it's true for any closed loop path that we make. So this is a closed loop because we're going to be moving from A to B, and then from B to C, and then from C back to A. That's the closed loop. So we have a displacement vector from A to B, which looks like this. That's delta R AB. We have a displacement vector from B to C that looks like this. And I need to draw these because we're going to calculate the work done. And then we have a displacement vector C to A. It goes like that. So let us calculate the work done by the force of gravity on this loop path. I guess we could start out by saying, is this really 0? That's what we want to find out. So the work done by the force of gravity in going from A to B to C and back to A again. That's what we want. So that's equal to the work done by the force of gravity in going from A to B plus the work done by the force of gravity in going from B to C plus the work done by the force of gravity in going from C to A. We can calculate each of those things. And we know what those things are, so we know how to write them, at least symbolically. The work is the dot product, or the scalar product, of the force vector with the displacement vector. And when going from A to B, we mean RAB. When going from B to C, we mean delta RBC. Oh geez, what did I do there? This is the force of gravity. And then from C to A, we have the force of gravity dotted together with the displacement from C to A. Now we want to calculate those. So let's take a look. So the first one, from A to B, is going to be the dot product of FG with RAB. Now we could write down, if you remember, the basic equation for work is, well, it's the dot product like this, but what that means is magnitude of the force, magnitude of the displacement, cosine of the angle between the force and the displacement. So we could do that here using the definitions that we have of these distances and heights. We could come up with some angles, and we could figure out exactly what the angles are between the displacements and the forces. But what I'd like to do is use something that's a little bit easier to work with. And if you remember, I defined last time that because of this cosine here, if you pair together the cosine like with the force, then you could write that thing as the force parallel to the displacement times the magnitude of the displacement, meaning the component of the force along the displacement. Or you can write it as the magnitude of the force times the component of the displacement parallel to the force vector. So these are vectors, I guess. And I think the second one will be really useful to us. Let me show you why. So if I want to find the work done by the force of gravity from A to B, then that's going to be, as we set up there, it's Fg dot delta RAB. But I could write that as Fg magnitude times the component of RAB, which is parallel to Fg. So what do I mean by that? Well, what I do is I take the Fg vector and I call that an axis. So I could call that like this axis here. So this is the axis, this is the parallel to Fg axis. And it's positive downward because that's the way I chose it. Then we look at the RAB vector, and the RAB vector looks something like this. And you see that its component is this number right here. Well, that number is a negative number, so let me just label that. That's going to be delta RAB parallel to Fg. That's the component of the delta RAB vector in the direction parallel to Fg. So because it points backwards compared to Fg, it's going to be a negative number. And you can see, well, if there was an angle, we could find it as the magnitude cosine theta. But if you look at the picture, what is this distance? Well, it's just h1. So I can write this as, Fg times minus h1, because that's the component of delta R parallel to Fg. So what do we get? Well, this is going to be, I could just write it as mg for the magnitude Fg. Sorry, let's make it a little bit more clear. So it's Fg times minus h1. And then I could do exactly the same thing for the other ones. So if you look at Fg and RBC, well, now RBC points downward, sort of. And if you were to place it on this axis and find its component parallel to Fg, it would be a positive number, and it would be projected along this sort of y-axis. So it would be exactly equal to this distance right here. Well, what is that distance? Well, that distance is h1 minus h2. And that whole work should be a positive number because you see that Fg points down and R points sort of down. Certainly the angle between them is less than 90, so that should be approximately positive. And then finally we can do the last one. So the last one is Fg times the component of RCA parallel to Fg. Well, this should turn out to be positive again, so maybe I can just draw it for you here. Here's delta RCA, and its component would be a positive number there. And what is that? Well, that's just exactly equal to delta H2. So this is going to be Fg H2. So what do we get? We get, let's write it as mg now, we get minus mg H1 plus mg H1 minus mg H2 plus mg H2. And it all works out very nicely. They all cancel out. So it works. So our question was, if I choose some arbitrary path and going around in a little circle here, I choose arbitrary points. I didn't talk about what H1 or H2 are. I calculate the work in going through that closed loop, and I find that the total work in going through the loop is equal to 0. That means that gravity is a conservative force. So what else can we say about this? Well, we gave two definitions for the conservative force. One was that the work is 0 through a closed path. The other was that the work is independent of the path if you go between 2 points. So let's take 2 points. Let's take our A and B, Now the work done from A to B, we calculated that. That was due to delta RAB, and then of course we have the force of gravity pointing like this. But the question is the work done as you go from A to B exactly the same along this path as it is around some other path? Well, we can show that by choosing some arbitrary point, C, and say, okay, I want to go in a different way. I want to go from A to C, and then from C to B. So that's an alternative path from A to B. Well, you can see that the work done by the force of gravity from A to B is equal to the work done by the force of gravity from A to C to B. And the reason is because we just showed that, because we used exactly these displacement vectors just in the opposite direction. And that just introduces a -1 in the calculation, and that means that this putting them on opposite sides of the equation here, I could move them back over to the other, and we'd get exactly that. So this is exactly equivalent to the work done by the force of gravity from A to B, plus the work done by the force of gravity from B to C, plus the work done by the force of gravity from C to A. And if those things are equal, then that would turn out to be 0. So these two expressions are exactly the same thing, as you can see in this picture. Going around once in a circle can be written as going in two different directions between two of these points here. So we can also say that a conservative force is one for which the work done between points A and B, whatever those happen to be, is path independent. It doesn't matter which direction I take. And of course, I'm only doing it for little straight displacements, but you could take an alternative path that goes all the way over here and calculate the work along that path. You'll find the same thing. So that's a conservative force. Before we talk about other conservative forces, let's do the potential energy due to gravity. So let's find it. So let me remind you of the definition. So we define it only up to the difference in potential energy. So delta U due to Fg from one point in space to another point in space is equal to minus the work done by Fg from that point to the other point. So this is our definition. Maybe I should put a box around it because it's important. That's the definition of potential energy. So let's figure out what that means. Well, if we take, again, our ball and we move it between 2 points, from point A to point B, we're going to move it, and in order to find potential difference, we need to calculate the work done. So let's look at the work, which is going to be done through the displacement and through the force of gravity. So at some point along the path, you could draw the ball with its force of gravity vector. So let's just write it out. So delta U Fg is equal to the work done from A to B, and that's going to be equal to Fg dotted with delta RAB with the minus sign out front that came from the definition here. Now, we could write down Fg delta R cosine theta, our definition of the dot product, but again, I'm going to use one of our alternative definitions, and that was the way that you can write it in components. So what I'm going to do is I'm going to choose a y-axis that points upward from the center of the Earth. And I'm going to use that those components in order to define my dot product, my scalar product. And if you remember, the equation it's just the multiplication of the components together. So it's Fgx times delta RABx plus FGY times delta R ABY, and then you could continue it if you had Z direction as well. So what do these things mean? Well, FGX, if you take the FG vector and you place it on this coordinate system that we defined, you see it has a 0 x component. So that's 0. Delta R ABX, that just means delta x. So there was some delta x along this thing, but because we're multiplying it by FGX, that whole term goes to 0. The other term doesn't go to 0. We have FGY. Well, FGY is negative, and it's minus the magnitude of FG. Right? If you take FG and you place it on this coordinate system, then this number is FGY, and it's minus FG. What is delta R ABY? Well, that is the y component of the delta R vector, which we just call delta y. So it's the delta y for the path. So what does this whole thing turn out to be? Well, it's going to be minus 0 minus mgy. So it's just mg delta y. Put a box around that as well. So our basic equation for potential energy, maybe I should erase the little g's here, then we see that it's really the basic equation for any conservative force. For the force of gravity turns out to be this particular expression, and I actually should put the box around one other thing, which is that the plus y-axis points up, meaning up away from the center of the Earth. So you can't do it for just any coordinate system. You have to choose the y-axis as pointing upward away from the center of the Earth, meaning in the opposite direction of gravity. And that gives us our potential energy due to gravity. Well, it actually gives us the change in potential energy, so we can make another distinction and say that the potential energy function, as a function of this y coordinate, is just mg times y, because delta u means ug final minus ug initial. So we could just say that at any moment in time, at any position, the potential energy has the equation mgy. And it'll turn out that it doesn't matter where you define the 0 position, and what that means is that you can place this coordinate system with the y-axis pointing upwards and the origin at any position. The origin can be anywhere. So that's our potential energy due to gravity. So let's look at our other important conservative force, and that is the spring force. And I'd just like to argue for you that the spring force is conservative. I won't make quite as complete an argument as I did for gravity. And that's just because it's harder for us to calculate the work done by the spring force. We talked about it last time, and the idea is that if you want to calculate the work done by the spring force in going from point A to point B, which is what I'm doing here. So just to remind you what's going on, we have a spring with a natural length L0, meaning that the spring is not pulling on the mass at all at this point. We define that to be our equilibrium. It is our equilibrium position, but we define it to be our x0 position. So we choose a coordinate system so that the x0 position is there. Then you pull the mass out, and that stretches the spring much longer than L0. And what that means is that the spring force will have a value. It will point backwards like this. And its magnitude, as we found before, is magnitude of the spring force is equal to some constant times L minus L0, which means that it's just going to be some constant times xb, the absolute value of xb. Now the problem is that as you pull this mass outward, the force changes. It goes from 0 force here, so Fs is equal to 0 when the spring is unstretched to some large backwards force here. And along the way, the force is getting larger and larger. So that means that we can't actually use the F dot delta R equation for the work, because that was only allowed to be used when the force was constant. So what we found last time is that we could calculate the amount of work done by breaking up the path into little segments along the x direction. So we can write down the spring force magnitude and the x position, and what that equation tells us, so Fs is equal to kx, what it tells us is that this is a straight line here, so at any particular value of x, you're going to get a particular value of the spring force, which is proportional to the amount that you've stretched it. And the work done is just going to be the sum of the works done over little intervals. So if you look at this thing here, effectively what we're doing is we're saying, okay, we're going to move it over some small delta r, which is some small delta x, as you go along this path, and we'll assume that the force is approximately constant, and we'll calculate the amount of work that happened over that little path, and then we'll look at the next delta x, and there'll be some amount of work in that one. And then if you add all of those rectangles up, then you get the total amount of work. So what is the total amount of work from A to B, so from the equilibrium position out to this position where it's stretched the furthest? Well, that is going to be, and we can just write it out quickly here, that is going to be the area of this triangle. So that's going to be, so work from A to B is equal to, well, it's actually minus the area that's shown here. So let's call this A1. And it's minus because the force is pointing backwards, so the displacement points in the opposite direction of the force. So we can calculate the sum of the absolute values of the work, and that's equal to the area of this triangle. And we found last time that that was equal to minus 1/2 k xb squared. That's what we found for the area of that triangle. Now, what if we do another step, and so we could go from point B to point C. So we could calculate the spring force work from B to C. Well, that thing will again be found on this little graph, but we'll be going in the opposite direction. So we have this triangle here all the way out to XB, but we're going to go now from B back to C. So we're going to do this here. And we're going to be moving in the other direction. So it turns out that now the force is pointing in the same direction as the displacement. So here we'll get some area 2, and the work done from B to C is equal to plus area 2. And then the next step, in going from C back to A, well, that one is the next one. I'll draw it again. So here's our little triangle going all the way out to XB, but now we're going to go, so this was XC, and now we're going to go from XC to A, and that's going to be this little triangle right here. So A3 is that little triangle, and the work done from C to A is equal to plus A3. Again, the work is positive in this motion from C to A because the force at this moment is some leftward pointing force, and the displacement over every little step is also leftward pointing, so you get a positive work. Okay, so what's the point? The point is that I've done a circular loop. So now my space is one-dimensional. I'm just going back and forth across this floor, but I've done a circular loop. I've gone from A out to B, back to C, and then back to A again. And the question is, what's the total work done? Well, the total work done is going to be A1 with a minus sign plus A2 with a plus sign plus A3. But if you look at these two pictures, what is A2 and A3? Well, we get, so the work total, let's write it out. Work total is equal to minus A1 plus A2 plus A3, which is equal to minus, well, A1 is just A3 plus A2. So we get minus A3 plus minus A2 plus A2 plus A3. That equals 0. So we've shown that the work done by the spring force is 0 over a closed path, a closed loop, and that means that the spring force is conservative. So we've shown it there. So what is the potential energy of the spring then? Well, we can write that down. So let's write it down specifically for taking the spring from the equilibrium position to some other position. We'll just call it x. So the equilibrium position, remember, is at x is equal to 0. So that means that the unstretched length of the spring is just this distance here. And then we're going to take the spring out to some other position, which we can just call x here. So what is the potential energy at point x? Well, the change in potential energy due to the spring force from x is equal to 0 to x is going to be minus the work done by the spring force from x is equal to 0 to x. Well, we know what that is. We calculated it last time, and I just showed you what it was up above. The work done is minus 1/2 kx squared. So that means that the potential energy difference in going from equilibrium out to x is equal to plus 1/2 kx squared. And if we just agree that we're going to keep this as our coordinate system, then that means the potential energy value at any point along the x-axis can be written just as the potential energy of the spring as a function of x is equal to 1/2 kx squared. And again, I should make a comment where x equals 0 is equilibrium. So this is our potential energy for the spring, right there. So we have a function that tells us the potential energy value wherever the mass has pulled out to, however much the spring has been stretched. It depends only on this x value, but you just like the gravity, it's not just any x value, it's the value that you get when you draw your coordinate system like this so that the origin is at equilibrium. So it's the amount that you've pulled the spring out. So I guess another way that you could write this that's independent of the coordinates is just L minus L naught squared, meaning the amount that you have stretched the spring squared. And that's our second potential energy function. So those are two conservative forces, but we shouldn't get the idea that all forces are conservative. So probably the most famous example of a non-conservative force, I mean, in fact, most forces are non-conservative, but the easiest to see is something like friction. So let's use the definition of conservative, the idea that the work should be the same over a closed loop path, to show that friction is not conservative. So what we'll do is we'll take a little mass. We'll assume that there is a coefficient of friction here. So there's going to be friction acting as this thing moves. So we can move the mass along the floor, and as it moves, there will be a force of kinetic friction that points opposite to its direction of motion and also opposite to its displacement vector, for example, from A to C. So what is going to be the work, for example, from A to C? Well, it's going to be the frictional force dotted together with the displacement. And what is that? Well, it's going to be the magnitude of the frictional force times the magnitude of the displacement times cosine of the angle between them. Well, let's draw that out for ourselves. Force of friction kinetic, delta R AC, and the angle between them is 180 degrees. So that's going to be times cosine of 180 degrees. So what is that equal to? Well, it's going to be, I guess, mu k times Fn. The mass is just sitting here on a flat surface, so Fn will be mg. So that'll be mu k times mg times delta r. Well, that's d1, as shown in the picture. And there's going to be a minus sign in front because of the cosine 180. So there we go. So that is the work in taking the mass, the work done by friction in taking the mass from point A to point C. Now, if friction were conservative, then I should be able to get the same value as I take the mass past point C, but then back to point C again. So bring the mass out to B, and then back to C again. Well, that's definitely not the case, because if I go from A to B, what I get is minus mu k mg. Well, let's write it out a little bit more carefully. It's going to be equal to the work done by the force of friction from A to B, all the way out to B, plus the work done by friction from B to C. So what is that? Well, I don't really need to calculate it because it's basically the same kind of thing that we just saw. As we go from A to B, it's going to be minus mu k mg times d, I guess d1 plus d2. And then as I go from B to C, well, we do need to draw this out to see what it looks like. I'm going to be going in this displacement here, delta r b c, and the force will be pointing opposite to the velocity at that moment, so that means the force points like this. Well, again, the force and the displacement vectors point in opposite directions, so therefore I'm going to get a negative work, which is going to involve this d2. So I'm going to get minus mu k mg d2. And you can see all the terms in here are negative, so it's definitely not a zero work done. Sorry, it's definitely not, I didn't want to find it equal to 0, it's definitely not equal to minus mu k. Sorry, let me give myself a little bit more space so you can see the important point that I'm trying to write down. So it's definitely not equal to minus mu k mg d1. That term actually appears right here, minus mu k mg. Jeez, I screwed it up again. That term appears right here, minus mu k mg d1, but then there's an additional term, the minus mu k mg d2, and another term, minus mu k mg d2. So this is greater than that, and therefore it's not equal to the thing that we found for the first path. So I sort of screwed up the logic there at the end. Let me repeat it. I wanted to check to see whether moving a box from one point to another, from A to C, is the same whether I do it directly from A to C or whether I do it from A to B to C, because we saw that conservative forces should have path-independent works. That comes about from the fact that any loop path is 0. And we found it's not true. If I just go directly from A to C, I get this value. If I go from A to B and back to C again, I get something larger in absolute value, this thing here, more negative, so it's not equal. So friction is not a conservative force. Now, what if we have many forces acting? So we could consider this little setup of like a, I don't know, a box sliding down a half pipe here. So if we look at it going from A to B, then at any moment along its travel, we could draw like the free body diagram for it, just to see what forces are acting. So there's certainly a force of gravity acting. There's going to be a frictional force acting as it slides along that surface. And then there's also going to be a normal force acting. So there's a normal force here. So let's consider each of those and whether they are conservative and whether we might be able to associate potential energy to them. Well, gravity, that was the first thing that we looked at. So gravity is conservative. So that means that we can say that the work done by the force of gravity is equal to minus the potential energy change due to the force of gravity. I guess I should write it as minus delta UFG. So we defined a potential energy. We could calculate that in order to find the work done by gravity over any 2 points. What about the normal force? Well, the normal force we didn't talk about yet, but there's something here that tells us something about the normal force. So it turns out that the normal force is not conservative. And that's because it's because that the normal force of this surface, well, it can point in all sorts of different directions, but you could also have normal forces of other objects pressing. So there's nothing in general that tells us that normal is conservative. However, in this case, we get something very special. Whenever something's going along a surface, its delta r vector must also be along that surface, right? The velocity points along the surface, the displacement vector points along the surface. The normal force always points normal to the surface, perpendicular, and therefore the work done by the normal force is 0. So it's Fn is not conservative, but it doesn't have any influence when we're calculating the work done by forces as an object moves around. And finally, we have the force of friction is not conservative. And we get that the work done by the force of friction is some negative quantity in moving from A to B. In fact, it's always going to be negative because work done by the kinetic frictional force points opposite to the direction of motion, opposite to the displacement, and that always gives a negative work. So we can imagine looking at all of the forces doing their work. The work done by the force of gravity can be represented with a potential energy function now. The normal force doesn't matter at all for the work, and the frictional force is going to be some negative quantity there. And if we added all of those up, then the net work, which remember is the sum of the works done by each force, well, if, for example, the gravity force, the work done by the force of gravity is larger than the work done by the frictional force, then we could get something maybe positive here. So this is if work by force of gravity is greater than the work by the force of friction. And that's because the work done by the force of gravity, since Fg points down and delta r points generally downwards, should be a positive number, which means that delta u must be a negative number. And the work done by friction we said is a negative number, so if the gravity work is more, then the total is going to be positive. Why am I saying that? Well, because we know something else, that the net work is equal to the change in the kinetic energy, which is the change in the velocity of this object. So it might have some initial velocity up here, but at the bottom it might have some final velocity which is larger because the delta k is greater. Now, all of those things are sort of vague as I've said them. We're going to make them precise right now, and the idea is to come up with an idea of conservation of energy. So the basic statement of conservation of energy is that if we account for all forms of energy, so those might be the kinetic energy of motion, 1/2 mv squared. I'll just remind you what that looks like. So K is equal to 1/2 mv squared. It might be potential energy, like for example, it might be Ug, which we said was mg delta y. It might be something called heat. So heat is something that you get when you have friction, or it might be some other forms of energy. If you account for all forms of energy, then it's a general principle of physics and of the universe that the total energy is conserved. And what we mean is that the total energy of the system does not change in time. So the total energy, its value doesn't change in time. It might move from one type of energy to another, either from potential to kinetic to heat, but the total value doesn't change in time. And we call that a conservation law, that the total amount of energy is conserved. Now we're going to deal with a more special case, which is when there are only conservative forces doing work. So if there's only, for example, gravity and a normal force, then the normal force is non-conservative, but the work done is 0. And gravity is a conservative force, so the only thing that does work is gravity. Then we can say that the mechanical energy is conserved. And mechanical energy is defined to be the kinetic energy plus the potential energy. So kinetic energy plus potential. And when we say potential energy, we mean the sum of all the potential energies. So the potential energy due to gravity plus the potential energy due to the spring. If only conservative forces are doing work, then we can say that the mechanical energy is conserved. And that will allow us to solve some problems. We'll do some examples in a moment. So what's the statement of conservation of energy? Well, we'll derive it. So let's imagine that we have an object that's moving through space and it has forces acting on it. So maybe it's like an object that's going down a hill, and there's going to be a force of gravity and a normal force, and maybe there's a frictional force, and I don't know what else. Let's leave it at that. So in any case, we have the net force is equal to some F1 plus some F2 plus some F3, etc. And what we're going to do is we're just going to divide up those forces into conservative forces and non-conservative forces. So maybe it's like F1 and F3 are conservative, and F2 and other ones are non-conservative. So these are conservative forces, and these are non-conservative. So we could say, let's give myself a little bit more space, we could say that the net force is equal to the sum of the conservative force 1 plus the conservative force 2, etc., plus the non-conservative force 1 plus the non-conservative force 2. So I haven't changed anything. I still have a free body diagram, the sum of all the forces acting on the object. I just decide whether they are conservative or non-conservative based on the tests that we've already done in the lecture today, based on checking whether they are conservative or non-conservative. So why do we do that? Well, what we can do is we can apply the work-kinetic energy theorem. And if you remember, the work-kinetic energy theorem says that the net work, meaning the work done by the net force, is equal to the change in the kinetic energy. So this means the work done by the net force, and this means kinetic final minus kinetic initial, where kinetic is always 1/2 mv squared. So in some sense, if you add up all the work, you can find out something about the change in the motion of the object, the change in its speed here. So let's do that here. So the work done by the net force equal to delta K, and that means the work done, the sum of the works done by each force. That's what we mean by the net force. But then we can use that grouping that we had, which is we can call some of them conservative. So work done by conservative force 1, conservative force 2, and call some of them non-conservative. So I've just grouped them together. Well, what do we get from the work done by the conservative forces? Well, we have a definition, which is that any conservative force leads to a change in the potential energy. And the definition was that the change in potential energy was minus the work done by the conservative force. So we're going to get minus the change in potential energy of the first conservative force, minus the change in potential energy of the second, minus, etc. And then this whole thing, we could just say that it's the non-conservative work. So we're just going to group all of the works due to non-conservative forces into something called the non-conservative work. And then we still have delta K here. We could also group, I mean, as long as we remember that we did this, the changes in potential energy into the total change in potential energy. So what I mean that we should remember it is when we come back to use this equation, we remember that this statement about U actually means you need to add up all possible U's that you have. So if you have a spring in the situation and gravity, then you want to include both potential energies. But for now, I'm just grouping them together. So what does this equation mean? Well, it means that we have minus U final minus U initial. That's what delta means. We have the non-conservative work. And then on the right-hand side, we have the final kinetic minus the initial kinetic. Well, I can group this entire thing into an initial and a final side. So on the left-hand side, I have plus U initial. So I can write U initial. I can add kinetic initial to both sides, so I have plus kinetic initial. The work conservative was on that same side, on the left-hand side, the work non-conservative. And then on the right-hand side, I have kinetic final, but I also have minus U final is added over there. So I get U final added over there, plus kinetic final. And this is the statement of conservation of energy. And I can write it in one other way, which is to say that the mechanical energy initial plus the work non-conservative is equal to the mechanical energy at the final. And when we say initial and final, we just mean at some initial time or at some initial position versus some final position, final time. So this is conservation of energy. And within this statement of conservation of energy, we also have a statement of conservation of mechanical energy. So because work non-conservative equals to 0 implies conservation of mechanical energy. So if there are no forces, if there are no non-conservative forces doing work, then you just get MEI is equal to MEF. We can use that. Okay, so we're going to do some examples now to show how to use this equation, because it's a new way of doing problems. Just like doing problems with Newton's second law or with relative velocity problems, you always want to start with the basic principle. So this equation that we've written down for conservation of energy, we're going to be writing that down, and we're going to be specifying what we mean by initial and final in our picture so that we can be very clear about what goes on the left-hand side and what goes on the right-hand side. So it's best to see that through some examples. So let's look at this one first. The baseball player hits a baseball straight up It leaves the bat with a speed of 25 meters per second. How high does it go? So this is a problem that we could have done back in the very beginning of the semester using kinematics tools. So here's a baseball bat hitting a ball, and it's a foul, I guess. So the ball goes straight up with some initial velocity, some initial speed, v0. So v0 is 25 meters per second. And it will go up, it will stop, and it will come back down again. So we can label that as a particular height, which we do not know. Is there anything else we need to show here? Well, I guess what we should show is what are the forces acting. And there's only one force acting. So we're going to assume that there's only the force of gravity acting on the ball as it heads upwards and downwards on its trajectory. And that will determine how we write down the work and how we determine what works are being done. Now, we could do this with kinematics. We could say, okay, there's an acceleration due to gravity that we know it's equal to g, and we could write down the kinematics equations in order to do that. But instead, we're going to write down conservation of energy. So we write it down. Mechanical energy initial is plus the work non-conservative is equal to mechanical energy final. Now we try and make it specific to our problem. So meaning I'm going to set my initial equal to A and my final equal to B. And what I mean by that are I'm going to start out here at point A and I'll end up here at point B. So now I can write out what my mechanical energy initial is. It's going to be the potential energy initial plus kinetic energy initial. The work non-conservative, well, I only have the force of gravity acting. That's a conservative force, so there are no non-conservative forces doing work, so I have a 0 there. And then mechanical energy final is U final plus kinetic final. Now I need to look and see what conservative forces I have that give me potential energy. And I look back at my free body diagram, I say I only have the force of gravity, so I only have that doing work. So I can write this as UG initial. Kinetic energy initial I can write as 1/2 mv initial squared. And then U final is UG final. And kinetic final is 1/2 mv final squared. Okay. Now I have UG initial, but I have an equation for the potential energy due to gravity, and that is mgy initial. That's my equation. Remember, UG as a function of y is equal to mgy. Now just writing that down should remind me that I need to specify what I mean by y. And y is an axis that points upward, so I should draw that coordinate axis, y. And I also need to choose where its origin is. And I'm going to choose the origin right here. So this is my x-axis. And I choose that because then I'm going to be able to say that, well, y initial is equal to 0. So we'll wait till the next moment to plug that in. But this quantity here will definitely be 0 because at point A, my initial position, the y value is equal to 0. Okay, so we have 1/2 mv initial squared. Well, v initial we called v0, so I can write 1/2 mv0 squared. UG final, well, that's mgy final. And then 1/2 mv final squared, well, up here at the top, v final is equal to 0. The ball stops. So I can write that whole side, that whole term, equal to 0. Keep plugging things in. Mgy initial, as we said before, is going to be 0 because it starts out at y0. I have 1/2 mv initial squared. That looks like a b there. I meant that to be a v0. And then we have mgy final. Well, what's the value of y final? Well, it's just h. So it's mg capital H. Okay, what are we looking for? How high does it go? What is h? So let's solve for h. We can divide both sides by m. We can divide both sides by g, and we get h is equal to v0 squared over 2g. And now I can just plug that in to my calculator. So let's see. So we have V0 is 25 meters per second squared. Square that. Divide by 2, divided by 9.8, and I get 31.9 meters. So it's a new method of doing a problem that we've been able to do before. Maybe you might consider it an easier method. I think that sort of logically it's easier. It's sort of easier to think about this transformation of energy from one form to another. You don't have to deal with components of vectors like we have to do with kinematics. So conservation of energy is just a scalar equation. You notice that there's no x's and y's here. And that makes it easier as well. So we'll do some problems that are similar to ones we've done before that you might think are with an easier method, or at least a different method. But we'll also do some problems that we weren't able to do before, and I'll try and show you why we weren't able to do that. So next example, we take a box and we kick it down a ramp. So let's draw a ramp like this. And we take a box that's up at the top of the ramp, and we kick it. Oh, crazy head. I guess it's after the kick, so there we go. Gotta put arms on the person. You kick the box and you give it some initial velocity, initial speed, and what are we told? It's 2 meters per second. And then the box slides, and it slides for a distance of 3 meters. So let's label that distance. So down here, it's going to have a final velocity of 0, because we're told that it stops at some moment. And what else do we have here? Well, the ramp makes an angle of 30 degrees. And anything else? We have a mass of 5 kilograms. And I guess that's it. So let's look at the box along its path and examine the forces that are acting on it, because we need to know that in terms of conservative forces versus non-conservative forces. So we're going to have the force of gravity, we're going to have a normal force, and we're going to have a frictional force. There must be a frictional force because that's the reason that it stops. So those are our 3 forces, but we're going to solve the problem with conservation of energy. So let's write it down. So mechanical energy initial plus the work done by non-conservative forces is equal to mechanical energy final. Let's specify what we mean by initial and final. So we'll just say going from A to B again, where the final position is B and the initial position is A. And we can break these apart. So mechanical energy initial means initial potential energy plus initial kinetic energy. Work non-conservative, well, do we have any non-conservative forces acting? We do. So normal, remember we said, is a non-conservative force, but you can see that it's pointing perpendicular to the direction of motion. So there will be no work done by the normal force. Friction, however, is a non-conservative force, and it will do work. So we need to write that down explicitly. So we say, okay, there's a work done by the force of friction. Then mechanical energy final is U final plus kinetic final. And then we have U initial is going to be mgy initial. And just by writing that down, I should choose myself a coordinate system. So I have to choose an upward pointing y-axis. That's my y-axis. And again, I'm going to choose it carefully so that one of my conditions goes to 0. So I choose it so that the box in the final position is at y is equal to 0. So I've chosen my coordinate system now. Kinetic initial is 1/2 mv initial squared. Work done by the force of friction. well, that's going to be equal to the force of friction vector dotted with the delta r vector, which I guess I should draw. So that's this vector here, delta r. And then we have u final is mg y final, and kinetic final is 1/2 m v final squared. So let's write all those things out. So mg y initial, well, it starts out right here. That's what my y initial value is. And I don't know exactly what that is, but maybe I can write it in terms of d instead. So this is some height here, h, and this is theta, and this is d. So I can say, well, sine of theta is equal to h over d, or h is equal to d sine of theta. So I can write my energy conservation equation now. Well, I can write it as mg times h, first of all, that's my initial height, and then I'll replace that in terms of d. My initial kinetic energy is 1/2 m, well, I called it v0 squared. And then my frictional force dotted together with my delta r, well, you can see from this picture here that the frictional force points backwards, the delta r points forwards. So I get minus from the cosine 180, I get magnitude of the force of friction, and I get magnitude of the delta r vector, which is what I call d there. The right-hand side is going to be mg y final. Well, that's 0 because my final position in the y direction is 0. And then 1/2 mv final squared, well, that's also 0 because the box stops. So I have 0 on both sides, for both terms on the right-hand side. So it's sort of like, you can think about this problem as, I start out with some energy, and we can think of that as both a potential energy due to the box being up high, and a kinetic energy due to the box being in motion. And all of that energy is lost, because in the final position, at the final time, there's no mechanical energy left. So all of the mechanical energy is lost. Where does it go? Well, it goes into the work done by the non-conservative force. It goes into the heat of the box rubbing up against the ramp. That's what this term is doing here. Okay, so the question was, what is the coefficient of kinetic friction? So that's going to be inside of here. I think I need to do a little bit of work to find it, because the force of kinetic friction is going to be equal to mu k Fn, and Fn, well, I have to do Newton's second law in order to find it. If I do Newton's second law, then I have this for a free body diagram, Fn, Fg, and if I choose for my Newton's second law this coordinate system, then we're familiar with the result, and I'm just going to write it down. It is that Fn is equal to Fg cosine of theta. So you really should do Newton's second law, Newton 2. But we're going to skip it for now. So what do we get? We get mgh plus 1/2 mv0 squared minus, and then I have mu k mg cosine theta. Mu k mg cosine theta, and then I also have a d here, is equal to 0. Is that right? I think so. So this was my frictional force. You see that I have a mass in every term, so I can divide through by m. And we're looking for mu k, so I could move that to the other side, and then I could divide through by the stuff that it's multiplying, and I get mu k is equal to gh. Oh, I was going to write out h in a nice way. So h, remember, is d sine theta. So gd sine theta plus 1/2 v naught squared divided by g d cosine theta. There we go. Okay, so we still end up doing some algebra and even some Newton 2 here. but we've arrived at a solution, so let's plug it in and see what we get. So we get 9.8 times d, which was 3 meters, times sine of 30 degrees. Then we add to it 1/2 times v0 squared, that was 2 squared. And then we divide by 9.8 times d, 3 meters, times cosine of the angle. And we find that mu k is equal to 0.66 approximately. That's our kinetic frictional force, coefficient of kinetic friction. So you see the basic method: write down energy conservation and then use it. And then as we go along, there were some things we needed to do. So work non-conservative led to a calculation of work for the frictional force. That's the topic of last time. Finding magnitude of frictional force in that led to the necessity of doing Newton's second law. I had to, when using mgy, I had to transform a height into the distance traveled around the ramp, and then the rest was just algebra to try and find it. One last example. So we have a child setting up a block on a frictionless track, so there's no friction here. Thank goodness. So we can get rid of that. So this is mu k is equal to 0 here. And the child is going to have a spring release for the block, and then it's going to go through a loop-de-loop. How far must the child pull the block back on the spring such that the block makes it around the loop? Well, let's address the last part of it first. So what does it mean for the block to make it around the loop? Well, it means that when it gets to the top there, that's a terrible picture. So let's look at it at the top. So at the top, here is our loop, and the block is going to be like this. So what does it mean for it to make it around the loop? Well, this is basically a circular motion problem. So let's look at that for a moment. So we have force of gravity pulling downward on the block, and we have the normal force of the track acting on the block as well. The block is moving with some speed here, and it must be accelerating because it's going around a circle. So we're told that it's a circular track. That's what the loop-de-loop is. Well, let's do that problem very quickly. So that is a Newton's second law problem with circular motion. So Fg plus Fn is equal to ma, Newton's second law. We choose our special axis for circular motion problems, the radial axis, and we write it down in terms of the radial axis. So Fgr plus Fnr is equal to mar. We find those components. So Fgr is negative, it's minus Fg. Fnr is also negative, it's minus Fn. And Ar is negative, but we know exactly what it is. That's what we learned in circular motion problems, that it's exactly minus v squared over r. That's why we choose the r axis. And finally, we find that, well, mg plus Fn is equal to mv squared over r. So that's our circular motion problem for the block at the top of the loop-de-loop when it's on the inside. So we're talking about right here in the problem. It's moving through here. So what does it mean that it actually stays, what was it said? That it makes it around the loop. Well, it's going to make it around the loop if the block remains in contact with the ramp. And the contact here is what's giving the normal force, right? There's a surface of contact between the ramp and the block, and that's what gives the normal force perpendicular to that surface of contact. So the idea is that it'll make it around as long as the normal force exists. And the fact that it just makes it around, so it just makes it if Fn goes to 0. So we can take the case of Fn going to 0, which is mg plus 0 is equal to m, and then we can call this v min squared over r. So that's the minimum speed it can have in order to make it a round. And you see that we get V min is equal to, well, you divide both sides by m and you get square root of gr there. So the case of the block going around means that it must have a speed at the top of square root of gr. Okay, so we've solved part of the problem now. Now we want to see how far must the child pull the spring back so that it does that. And what's the connection? Well, if you pull the spring back, then you get potential energy in the spring, which is 1/2, let's write that down. Potential energy for the spring is equal to 1/2 kx squared. That depends on how much you compress the spring. And that potential energy, when you release the spring, will lead to kinetic energy of the block here, and then the block will do the loop-de-loop, and it'll end up here with some different velocity than it had here, because now it has to deal with potential energy due to gravity. We don't need to deal with each of these things separately. We just need to take a case A and a case B. So let's sketch that out. So case A will be when you push it back by amount d. So it starts out here, and then B will be up here. And we just need to connect mechanical energy between those 2 points. So we get mechanical energy initial plus work non-conservative is equal to mechanical energy final. Mechanical energy initial is potential initial plus kinetic initial. Work non-conservative is 0 because I don't have any friction here, and because the normal force acts perpendicularly to the motion, so it does no work. And then we have potential final plus kinetic final. Now, potential initial, we need to be a little bit more careful than we have in the past because we have 2 possible potential energies. We have potential energy due to gravity, and we also have potential energy due to the spring. And then kinetic initial is 1/2 m v initial squared. And then for the right-hand side, we have the same thing. So we have potential energy due to gravity final plus potential energy due to the spring final, and we have 1/2 m v final squared. Now we can see what these things are. Well, for gravity, we need to have a y-axis. So we choose an upward pointing y-axis, and we're going to place its origin down at the initial position of the block. At the final position, it's going to be up here at a height of, I guess this is 2 times r. So we can write UGI as mg times y initial, which is 0. Now the potential energy to the spring I. Well, what we say is we're going to compress the spring by a distance d, and we're looking to figure out exactly what that is. So we write the initial potential energy of the spring as 1/2 k d squared. Then we have the initial speed as contributing to the kinetic energy, and that initial speed is 0. So we can say that that initial kinetic energy is 0. Then we have potential energy due to gravity final, and that's going to be mg times the final y, which we said was 2 times the radius of that circle. And then we have the final potential energy of the spring. Well, so the delta L of the spring is equal to 0 in the final position because you compress the spring and then let go of it, and then the spring is again uncompressed. So in the final case, the spring potential energy is 0. And then we have 1/2 mv final squared, and the final case is up here at point B, and that was the speed that we needed here as square root of gr. So that's going to be equal to 1/2 m times the square root of gr all squared. So what does that lead to? We have 1/2 k d squared, the rest was 0, is equal to 2 mgr plus 1/2 m, and then we square that and we get gr. So we get 1/2 kd squared is equal to, well, 2 is 4 divided by 2, so this is going to be 5 divided by 2 mgr. We're looking for d. Multiply both sides by 2, and we get d squared. Divide both sides by k is equal to 5 mgr divided by k. Or d is equal to the square root of 5 mgr divided by k. And now we can plug in. So what's our answer? It's going to be the square root of 5 times the mass. So we were given the mass in our original picture, 100 grams. So times 0.1 kilograms times 9.8 times the radius of the circle, that was 10 centimeters, so times 0.1 meters. And then we divide by k, and k was also given to us. It's 30 newtons per meter. So it's going to be divided by 30 newtons per meter, close the square root, and we get that d is equal to 0.13 meters, or 13 centimeters. So in order for the child to get the block to go around the loop, you have to compress the spring by 13 centimeters, and then due to this spring constant, it will shoot forward with some initial velocity, which we didn't even calculate because we're not interested in what happens in between. Given that initial velocity, it will make it up to here, and it will have the speed necessary so that the normal force does not break, or just barely breaks, and that means the block can go all the way around. So you see, it's nice. We don't have to deal with all the intermediate things. If you tried to do Newton's second law here, imagine what happens. The free body diagram is changing as you go around this circle. So doing Newton's second law would be very difficult. You'd have to do it many times. But we don't have to do that. We just take the initial position when the spring is compressed and the final position when the block is going through the top of the loop. And that's how we do a conservation of energy problem. All right, I'll see you next time.